Ladies and gentlemen, my name is Georg Ostermeyer. It's a pleasure again for me to be here back at AsiaBrake. Today I would like to talk about friction in general. In the end, you should be able to create your own friction model tailor-made for your application. Here's a plan for this lecture. On the introduction, I would like to go into a little bit more detail about the classical representation of what is known as Coulomb's friction, and in particular explain how the name came about historically. Subsequently, I would like to present the meaning of Coulomb's friction a little more plastically. Please keep in mind that worldwide this friction modeling is almost exclusively used in the simulation tools of the brake industry. Afterwards, I will talk about brake friction and explain possibilities of data science in this context, which each of you can easily use. The history is certainly very old. The maximization of friction was actively used, for example, for making fire in the Stone Age. Minimization of friction by lubrication can be found in drawings of the Egypts 7,000 years ago. Wheel techniques in transportation are about 3,000 years old. The systematically documented observation of friction starts approximately with Leonardo da Vinci in the 15th century. Here you can see drawings from him from different codices. Over the next 200 years, a series of scientists followed. Their findings summed up in 3 statements. Friction is proportional to normal load. Friction is independent from the contact size, and friction is independent from velocity. You see here below a principle set up to confirm this experimentally. Driven by gravity, a body is pulled on different sides of the surface. Its weight is a normal force. Independent of the position of the body, the velocity profile is always the same. Let's go back to Leonardo's drawing. Obviously, he draws such a testing machine here. Did he knew about friction? Sure. Did he knew these laws? We don't know. Did he perform these experiments? We don't know. One did not make at that time physical, but most mental experiments. From these considerations, however, he already invented a ball bearing which was rediscovered again 4 centuries later. So he knew a lot on friction. The 3 statements about friction were then historically assigned to Coulomb and called Coulomb's laws of friction. Here are some basic terms for the so-called static and kinetic friction. The Greek letter mu was introduced by Euler in 1750 and is still used for this purpose today. Here, the friction coefficients are plotted against the friction velocity. Let's take a closer look. On the right, you see the same plot as on the left, but rotated so that the 3-dimensional structure becomes visible. Plotted vertically, u is multiplied by the normal force, which is, of course, the friction force. Plotted to the right is velocity, and plotted to the rear is the traction force. For v equals 0, adhesive properties, that is static friction, are plotted. This ensures that a stationary body can be held by the ground up to a limit load. If the body moves, the floor will exert a constant friction force on the body. Is the friction law from Coulomb? No. Coulomb knows that mu depends on velocity. Is it a law? No, it is not a law. It is a model. And It is not realistic either. If you look at metallic contact, for instance, you find something like this for mu over speed. With an elastomeric context, for example, tires on the road, you will find something like this. And with lubricated contacts, you get a famous Stringer curve. Such curves can be found in brakes, but only in quasi-static measurements. That are measurements at constant speed. If the speed changes during braking, which is what the brake is for, the curves can look completely different. For brakes, this can be seen in the Akamasa test, for example. But this can also be found with other contexts. Next to the Akamasa, you can see a measurement at the rail wheel contact of a railroad. The diagram essentially corresponds to mu versus velocity. Here, more precisely, the slip force is plotted versus the slip. Dynamic measurements show a dynamic behavior of mu. For this, we need dynamic friction models. Let's get back to the basic. It is worth taking a closer look at Coulomb's friction model. Coulomb friction, strictly speaking, is defined only for point contact. For this, I would like to go into an energetic side of friction, a little bit more precise. Please note the definition of mu on the right side. If the numerator and the denominator are multiplied by the velocity, mu can be interpreted quite differently. Mu is the friction power in units of a characteristic system power. More precisely, system blind power, since normal force and velocity are normally perpendicular to each other. In this picture, one can ask approximately which part of mu goes into heat production and which into plastic deformation and so on. In any case, energy flows from one body to the other. Let us analyze these a little more closely. Imagine that we have a floor on which single mass oscillators are standing. They are just a symbol that the floor can absorb energy. Now we press the upper body onto the floor. It presses in part of the single mass oscillators. If the body is now moved tangentially, compressed single mass oscillators constantly run out of contact. The energy that remains on the ground is constant. It depends only on the normal force. It is independent of the velocity of the body. It is an almost perfect Coulomb friction. One can even explicitly calculate the friction coefficient. Only one property is not fulfilled. The friction depends on the contact size of the body. The larger the body, the less the body sinks in with the same normal force, and the outgoing mass oscillators oscillate with small amplitude. This is a problem, scale problem. But which contact area is meant by the Coulomb laws? Coulomb means the parent contact area, which is of course independent of the normal force. This does not apply to the true contact area, which is formed by the asperities of the bodies. This true contact area depends, of course, on the normal force. The body in our model is thus described an asperity. This asperity brings a specific energy into the ground. This defines a new value. Now let's bring in a second asperity. This has the same form, consists of the same material, everything is exactly the same as with the first asperity. However, since the second asperity encounters a different energetic state on the soil, its energy conversion is different, so it also have a different mu value. Although everything is the same with these asperities. The mu values, or the mu value, is a process variable. It is not given by the material and the geometry of the surface alone. So, as a real body, one has many asperity contacts. At each one, one finds a local mu. Also, the body as a whole, of course, has an energy loss, which defines a global mu value. But this is not equal to the local mu, but a complex sum function of the friction effects of the mesoscopic scale. Here I have shown the difference between microscopic and mesoscopic friction coefficient, that is, between global and local mu in a rigid body diagram picture. The same goes with brush models or finite element models. Because of the viscoelastoplastic properties of the body, the microscopic mu value cannot represent Coulomb friction. This would only be possible if the body and the ground were absolutely rigid. Coulomb friction, therefore, describes the point contact. But let's move on to brake friction. This is the basic layout of the disc brake. The brake pad is pressed against the disc, and in the process, a boundary layer film is formed not only between the lining and the disc, but also on the entire disc friction track on the disc. The topological surface structure of the pad shows a highly complex dynamical behavior. Let's take a closer look on brake friction. The simplest material structure of a lining is outlined here. Sand grains are bound into a polymer matrix. Let's look at a small section of this lining, which contains only one sand particle. If the gray cast iron disc is pressed against it, a patch around the sand particle is formed, which can be seen in the REM picture on the right. How does this work? First, the polymer matrix is rubbed off the disc until the much harder stone particle reaches the surface. This particle has a much greater wear resistance than the surrounding matrix. With the wear on the polymer matrix, the particle is pushed more and more into the matrix. With the sand particle, the normal force increases, and with it, the frictional force and the temperature. The high normal pressure between sand particle and rotor causes wear also on the rotor surface. This set of wear particle from the pad and from the rotor accumulate in front of the sand, in front of the sand rotor contact, exactly, and is compactified. Heat and chemistry causes melting and even alloying processes. Result is a triple coating of the compactified particle set, so a rather hard patch is born, which grows and carries by this more and more of the friction load. Of course, the growing tribological load will cause the patch to develop heat cracks and limit the lifetime of the patch. At the end, the patch will be flushed out of the boundary layer. In special cases, this can be seen from the two maxima of emission. They are the abrasion particles from the polymer matrix, the fragments of the patches. The surface of the pad is thus divided into parts. Type 1, the soft polymer surface with nearly no dissipation, and type 2, the patches with a breathing total surface area, which is essential for determine the frictional force. Birth and death of these patches can be seen as part of a cycle process. The input power produces friction, the friction produces heat and wear, and the wear produces particles which, together with the heat, cause the buildup of patches. The wear itself limits the lifetime of these patches. Increasing the patch area causes an increase in friction power. Decreasing the number of patches causes a decrease in friction power. See the functions F1 and F2. This process, which has been greatly simplified here, can be seen as a closed loop or closed control loop that provides a time balance equation of friction. You can see such a balance equation on the right. This is the friction law mine that describes mu dot as a function of heat and wear. If one discretizes the boundary layer and feeds it locally with geometry, materials, and local thermodynamic processes, one obtains a patch dynamics and temperature distribution as found in real brake. This patch dynamics is very stable. Self-organization effects we found many other driver contacts too. For example, on artificial hip joint shells or on railroad tracks where these patches appear as hardwired layers, at least, causing this periodic ripples in the rail wheel contact. Please let us look into the frequency content of the friction coefficient. The geometry dynamics of the patches only describe a rather slow dynamic of friction, as it can be seen, for example, in the Akamasa test. But there are also high-frequency time signals to be found, such as those that occur in the well-known MH phenomena. You see here a single patch. This can move on the polymer matrix. It can be regarded as a single mass oscillator. Of course, there are many patches on the surface and correspondingly many oscillators which can perform self-excited oscillations during the frictional contact. These mechanisms are stick-slip effects, mode coupling effects, thermoelastic instabilities, and even thermochemical effects. However, these oscillators are not independent. They are weakly coupled via the matrix. This has fundamental consequences. On one hand, the coupling depends on the size and distance of the patches to each other. This is defined by the load history. On the other hand, synchronization effects are possible due to the coupling of the oscillators. Two extreme examples are plotted here, ranging from a fairly smooth friction signal to macroscopic stick-slip behavior. The frequency signals can reach resonators in the brake outside the boundary layer or in the axle, and thus initiate a macroscopic MVH signal. To describe this, one needs dynamic friction models. There are some friction models in the literature which are defined by differential equations. In 2001, I requested a look for friction in terms of a balance equation. This results in a second-order ODE system for friction in 2001, which was especially formulated for brakes. In the second-order model, several time constants are included, which represent individual dynamic phenomena of friction on different timescales. On the left, for instance, measurements have been made by Kröger, Littner, and Popp on a very simple friction system. On the right, you see simulation results with a second-order friction law showing all effects of the measurements. This model can also reproduce Ericsson's measurements of the brake friction in 2000 very well. Both the hysteresis effects and the scatter plot for friction can be easily explained. But also the slip force slip diagram of the rail wheel contact can be calculated very well with this model. In particular, one can see that the apparent loops of the friction versus speed can be directly explained by the dynamics of my energetic model. So how we can develop better friction models? I would like to explain this to you here on the basis of the third order friction model. You can see here the factors and variables that we want to consider in the friction description. Black are the variables I considered in 2001. Now, the variable to the wear flow is to be considered as well as a disk temperature. Originally, only the patch temperature was considered by me, which has nothing to do with the actual disk temperature. Here you can see the assigned influences which decide whether the quantities belong to the function f1 or to the function f2. Thus, an equation for mu dot can be set up, but one must also consider, of course, the dynamics of the quantities themselves. Balance equations have to be set up for these variables too. So you can see that the equation for the patch temperature now naturally includes the disk temperature. For the wear particle stream, you see a rather simple approximation. This can be improved. I will not go into that at this point, but please see the paper coming out soon. The disk temperature itself is generated by the friction contact, but this equation is not part of the friction law. It is actually just a very simple model of the rotor. Here you can see some examples of simulation with this extended friction model for the Akamaster test. Cycle 3 is recalculated here with regard to friction value and disk temperature. The same for the pressure sensitivity cycle. The simulations show a good conformity. Also, the simulation of the brake squeal noise test is possible. Here you can see the measurement results in black and the simulation in red. Note that the brake model continues to run even outside the actual friction times. Here, especially the dynamics of the disk temperature is responsible for this. Here we have used the second or the third order friction model as a macroscopic friction model. In fact, on this scale, one would still have to take into account both the humidity and the reservoir dynamics of the brake dust. This will be shown elsewhere. But however, you have to determine your friction models. You have always to take account the coefficients. You have to determine the coefficients in your equations. Here I would like to show you an ingenious, simple way to do this. The idea comes from Brunton in 2015. Here it is shown for friction model. You want, after all, dynamic friction models, that is, a system of equations from mu. You have measured values over time. You see here a linear system of equations. We get the left side by numerical differentiation of the measured values from mu. The matrix contains parameters and measure values which are all known. If we calculate the vector xi on the right, we just get the model we are looking for. The system of equations is not a quadratic one, of course, so we have to use a standard least square method. If we use this with a regulation term, we can even achieve that the solution vector xi, which contains the required constants, is only weakly filled. Also, one can introduce new function on the measured values into the matrix and inquire over the vector xi whether these new terms can occur in the equations. If xi is zero at this point, then this term is not contained in the search friction model. I would like you to show this with a simple model. It is a third order differential equation system like our friction model. Since we have no measurement data, we produce some. To do this, we first generate solution data with the system and noise them, so they can be interpreted as measurement data for the system. You can see this 3 time signals in the plots below. Now we completely forget the equations and ask if we can get a dynamic model only from the data below. For this, We have to differentiate the time series numerically in x, y, and z. We fill the matrix with our measurement data. We bring in further functions. X, Y, Z, I'm sorry, and further functions like x squared here and 1. These are candidates to request for the structure of the possible differential equation, which should be clarified by the solution of Xi. The Xi vector should give us the coefficients of the model, and the coefficient for x squared should be 0, of course. This was not included in the model with which we produced the measurement data. Here you see the solution. Xix, Xy, and Xz. For Xx, you find only 2 entries. For x, minus 0.1, and for y, 2.0. This corresponds exactly to the initial equations for x dot. This is also true for the y dot and the z dot equations. So we can not only easily determine the parameters of our models from measured data, but we also have the opportunity to ask whether considering other terms makes our model even better. This is one of the ways in which data science techniques can even be used to generate new tailored friction models. Please let me summarize. Coulomb friction is a model, not a law. Coulomb friction describes a point contact on a microscopic level. If one goes up to the mesoscopic or even macroscopic level, more and more material properties and dynamic effects must be taken into account, the influence of which can be described by dynamic friction models. Data science and AI will be the future drivers in the development of complex brake models. Today, I could only touch on this here, but data science offers great opportunities both for clarifying physical effects, but also for misinterpretations. Perhaps next time I will be able to present these fantastic possibilities in more details. Thank you for your kind attention.